start.
Yeah, perfect. Thank you.
Yeah. So in general, the talk should be interactive. So people have different protocol of interaction, but if you can just like post message, I'm not sure it's maybe a little bit hard for me to see message somewhere because it doesn't appear automatically. So you just unmute and speak, and just feels like we're in the same room. That's kind of the same way, easiest way to interact. Yeah, just feel free to ask questions at any point. I really like this kind of conversational talks. Yeah, so yeah, so I'm Chenglong. I'm a PhD student in University of Washington. I work with Alvin and Ross, mostly on program synthesis, but also I kind of very interested in the area of like applying program synthesis to make it easy for people to interact with data. And it happened here that data visualization is a good way to interact with data. So I'm trying to make it easy for people to create data visualizations. And here comes a talk about how we actually understand data visualizations and how we design tool to try to make it easy for people to access data. So this is a work collaboration with a lot of people. For example, people from Santa Barbara and Austin, and people in UW and Berkeley. So data visualization is not a secret. Everyone knows it. So for example, like business people use visualizations to view future of the data, to understand what's the trends of things going to lay out, and understand performance rating for its department. And they're also for the purpose of presentation. Like when social scientists take a survey, they want to kind of show you what they discover. And visualization is one of the most efficient way to convey the idea of data. But today I'm not going to talk too much about how to design good data visualizations for those tasks. I'm going to talk about what is data visualization and how to make it easy to create visualizations. So it's kind of interesting like for us to think what is visualization, because we think it's very by default. We don't even think about the definition, but here it comes. So if you think about visualization, this is one of the early definition of data visualization. It's called a transformation of the symbolic to the geometric. I also find this a very good way to talk to PL people, because this what we love is to talk about transformation, talk about arrows. So this is data visualization. So the data visualization is essentially a mapping from symbolic data to a set of geometric objects. And the mapping, for example, what we do in our real life can be a visual program implemented in ggplot2, matplotlib, or Excel, or anything. So if you look at this, like a table is something we're familiar with. It's kind of relational data. So here is a very simple data set, contains two columns, column A and column B. And the mapping is a mapping by itself. It's essentially mapping a columns in the table to some attributes of the data visualization. So for example, here we can map the column A to X positions of the bars, and we can map column B to heights of bars. And if you get this, we get a set of geometric objects. Each row will essentially corresponding to a bar. And this bar will just create a data visualization if you render with some of the visualization engine. I mean, there are different ways to present it, but what this visualization presents is just a set of bars. So this is how data visualization is defined, and this is how we implement it. But in practice, like we don't just need this visual program to create the mapping from the data to geometric objects. So for example, now I have a more interesting data set, contains 4 columns instead of 2. So I double my data size. And I have there is an X column and now 3 like attributes A, B, C to show something. And instead of creating a boring bar chart, I want to create a stack bar chart. So for example, I want to understand how each portion contributes to the total, like for each ID. This stack bar chart is an easy way to present those kind of multi-category data. And now if you think about how do we actually find a mapping from the table to the bars, it's a little bit unclear. So if you think about here, like we have 3 columns. So when the visualization has 3 attributes, has X, height of the bar, and also color of the bar, right? The 3 attributes. But we have a table of 4 columns. It's a little bit unclear how do we do the match. So for example, it's pretty clear for us to understand we can map the X column to X of the bar, but it's not really about like how to map the column A to something or something. So there is a problem. So, and this actually is a problem in practice whenever we want to do data visualization, is that we don't just need a mapping to map data to the geometric attributes, but we actually also need a data adapter to adapt our data set. So if you think about this case, right, if we want to visualize our data set with 4 columns, X, A, B, C, and we want to create this stack bar chart I showed you earlier. So first, in reality, if we want to visualize using R and ggplot, it's one of the very popular framework for data visualization. What you need to do is to first apply a gather operator. So to obtain a table in this kind of like narrow format. So what gather do here is essentially it's going to turn the column names ABC into a key column. So if you can see the red part, it's going to be turned into the red part. And at the same time, it's going to move all the values to the associating key and X indexes. So essentially, we are just like rotating the table so that the header is going down to the key column, and all the yellow value are going like together with those after this reshaping. So if you see this 1 and column A, and the value is 1, then we're going to get a tuple, the 1A1. And after we get this is good because we're expecting 3 columns for 3 attributes. And there's where we kind of perform this mapping from the data to the view attributes again. And now we map x-axis, x column to the x-axis positions of the bars, and we map the key column to the colors, and the value column will be the height. And again, if we apply it to some visualization engine, you will figure out how to color them, what color to use for each category, and it will figure out how to stack them. But this essentially create the semantics we want for this data visualization.
Good question.
Yeah.
What is the limitation of, say, creating just another column that is just the sum of all the existing rows?
Yeah, that is good. In that sense, you get the total of the bars, but you lose the how to kind of do a segmenting for each bar, right? So you don't just want to see the total number of all categories, but you also want to see how much does each category contribute to the total.
Okay, I guess like I see your point there in that if we just added another column, it wouldn't really lead directly to the visualization we're looking for. Mm-hmm. And so what you're trying to do, or what you are accomplishing here, is kind of providing this sense of like hierarchical importance in this particular transformation.
Yeah, exactly. Yeah. So
okay.
Yeah. So if you think about the original table, it's more like, so actually what I typically refer to those 2 shapes of data set. So I mean, they are presenting the exact same information. There's no difference. All the columns correspond to, or each cell in the original table corresponds to a cell in the new table. But the only difference is that the first one is more compact. This is the way we like to see it in Excel or visually that human. And the second way is more like structural, as it's easier for the computer. So this essentially create a little bit of gap between how people want to see data and how computer want to see data. Yeah.
Thank you.
Yeah, cool. Yeah, so this is how we do this in R and ggplot2. And this is essentially just like how the practical data visualization process is different from the theoretical directly mapping from data to the geometric objects. We actually need, besides need a 5V to do the transformation, we also need a data adapter to transform the data depending on what visualization we want to create. So in practice, like for us, a lot of people use programs to do the data visualization, like Python or R to do transformation. And for visualization, we use ggplot2 and VegaLite or matplotlib. For me, I typically use 2 separate tools. I do most things in Python, and then I visualize using VegaLite. That's kind of easy. But like R and ggplot2 is another popular way people do it right now. So using those tools is actually, if you view this pipeline, it actually creates some like difficulties for people to actually create data visualization. So first, you need to be familiar with both data preparation libraries and visualization libraries in order to fulfill this pipeline, right? You need to know what visualization function to use and how to transform the data. And especially for the data transformation, it may seem pretty easy when you see someone do it, but when you are actually trying to do it, it's not that clear sometimes because you don't know what the resulting shape looks like. So actually in a previous study, I think that one is mostly focusing on some like analyzing some experimental data, and this shows some reshaping and aggregation of data actually requires a lot of like practice in data transformation to be able to do it properly. And there is another point. is that now we are choosing the visualization function. There is a dependency between the data shape we want to present and the data transformation we want to need. So if you think about this, if you want to switch from like what we said earlier, right? If we want to have a total column to show all the bar, and now I want to switch into like a bar with stack bar instead of having only the total number, then we essentially need to use a different data adapter to transform the data. This means whenever you process the data, you have a little bit more work to do. And those are the challenges when we were inspecting the pipeline. And in practice, all these challenges happens. So this is a very interesting survey about why like social scientists don't have a widely adopt data visualization to present data. So this paper is kind of like interesting. They're trying to advocate social scientists to use more visualization to show their data instead of presenting in their paper. So there's some fun take when chatting to some social scientists, and especially the old school social scientists. If you read their paper, they typically have a like 2-page just containing 2 tables to show all the data. But now some like newer generation social scientists are preferred to create some plots to summarize them, so it's easier to visualize. And this paper is essentially arguing like why is it hard to do it and what people should do. And there are some very interesting parts to discover by this survey. So first, all the data comes into different layouts in practice. So for example, if I'm exporting data from one of my particular software, or I'm downloading data from some public database or from government document, then the data layout have very different styles. And because they're created by different people. And the second thing that because they're not like a professionally trained software engineer or they are not like very good data scientists, they don't have that much software knowledge. So they are typically relying on some of the tool they learned from school or some tools like provided by the library. This means they cannot really do a freestyle visualization with whatever language they're familiar with. And finally, they are not trained to be like visualization experts. So if you want to talk about stack bar chart versus bar chart, sometimes they're not able to figure out the difference in the API. So this means like adopting the visualizations can be hard, and there are some like barriers. So what can we do? So if we want to think about, if you want to design a new pipeline to create a visualization, how do we avoid those 3 barriers for people to create data visualization? So let's first think about that, because we know the data layout comes from different sources. It's something we cannot control. We cannot normalize the whole data in the universe so that they're easy to visualize. So the best hope is that we can design some tool that the user specification is independent of the data layout. So it means whatever data layout it is, I don't need to worry about what's the input data shape. I'm hoping that we can still describe what we want to visualize. And the second perspective that we hope the user don't have to know that much about data visualization to specify the visualizations. So yeah, so have those kind of visualizations. And the third point is that for the best hope, we hope there is no programming, because not everyone is able to learn programming to the degree that they're able to create data visualizations. I see some message. Let me see what it is.
I can read it out for you. It just says, I have a question. Is the mapping generally invertible? Is the mapping always 1-to-1?
Not always. So actually, I'm going to some point about this a little bit later still. So, but in a lot of cases, it's has a direct correspondence, but not always invertible. Yeah.
Thank you.
Let me see. I need to close the window, otherwise it will block some of my view. Yeah. So yeah. So hopefully we have a specification that allows it easy for people to interact with the data without worrying about the data layout or the visualization knowledge. So how do we find out those kind of specification? We actually did some very interesting interview with a bunch of people in our department to say the way of like getting it this way is that we show them a visualization task. Instead of asking them to solve the visualization, I asked them to explain to me if they want me to solve the visualization. Can you tell me describe what I need to visualize? Essentially, if you think about the model, I'm telling the person to describe the visualization process to someone. And in that way, they are going to describe what they want. And one common way, it turned out, one of the most efficient way for them to show their idea is to create those kind of sketches on paper, on whiteboard. And if you view this kind of detail, what is actually in this sketch? The sketch is actually a partial visualization that shows the purpose of the intent of visualization is provide a subset of geometric objects of the final visualization. They're essentially telling me that my visualization should contain those few rectangles. Can you figure out a visualization that contains all of them? And it's funny enough that when we look into a Stack Overflow, actually a lot of people asking visualization questions asking in a similar way. They create a sketch of the visualization with some partial elements, and then they're hoping the expert is going to create a full visualization that contains all the partial elements. Especially if you think about like Stack Overflow, it's not a very friendly interface for us people to upload, but people still take the effort of writing down the sketch, take the photo, and upload. It actually kind of shows the power of doing this sketch and providing partial visualization too as a way to specify the visualization intent. So based on this kind of observation, we're just thinking about a paradigm allowing people to do visualization by example. So instead of like asking people to create programs to transform the data and visualize the data, what people will do is to provide the input table and create a demonstration to show a partial visualization. And it's essentially asking the programming synthesis tool to figure out the transformation program such that the final visualization contains all the partial elements. Yeah, so the blue parts are the input. The user provides a table and the partial visualization. You can think in terms of like a sketch. And the idea is still to synthesize a program so that everything generated by the program contains every element created in the partial program. Let me show you a concrete example. It's a little bit hard to see in those symbols, but also some people like those kind of symbols. So yeah, so for example, a user have our data set of 4 columns, X and ABC. And this is the goal of the visualization. We want to create a stack bar chart to have all the bars stacked together for the same x-axis values. And what the user will do, the user will create a partial visualization. The partial visualization, for example, are 2 bars that will appear in the final visualization. If you render those small 2 bars in the plot, you get this tiny visualization. And what the user asks the computer is essentially to find a visualization that contains all the bar, and the visualization should be derived from the input table. And what this is the objective. And what the computer will do, the goal is to essentially figure out those 2 transformations. The transformation of the data layout and the transformation of the visual elements to create the final visualization that contains the demonstration. Yeah, this is the requirement. We require the output contains the partial visualization provided by the user. So this actually brought up some very interesting program synthesis challenges. So this is why I'm calling about like theory part. Yeah, there's some questions. Let me take a look.
I think Alvin was just answering the question in the chat with text. So.
Oh, I see. Okay.
Don't worry about the chat. If there's a question, I'll speak up. I'll read it.
Yeah, sounds good. Yeah, so this is the goal. I want the tool to derive those 2 red parts, and the user only need to provide the blue parts. Oops, it's overlapping on my screen. I need to close the chat window. Yeah, so the first challenge for the program synthesis task is that the synthesizer needs to now synthesize 2 programs together instead of 1, right? We need to figure out a visual program from the visualization language, and we also need to figure out a data transformation program in the table transformation language, so that we actually need to synthesize programs from 2 languages. And second thing is that the user can potentially provide large input table. Actually, why is this a challenge? If you think about the traditional program by example tasks, what people will do is to craft a small input table and a small output table and ask you to find a program. But here we're asking user only to provide a partial output, and the user can use whatever input they want to provide. And so the input table can potentially be large. And last, compared to like traditional synthesis problem is asking you find a program that turns input to the output. We're asking the output to be a table that contains the partial demonstration. So this is actually a weaker specification that impose some challenges for program synthesis tools. So the first part, like how do we address those difficult problems in program synthesis? So our insight is actually to break down the synthesis problem into two processes. So the first is to decompile the data visualization. So instead of synthesizing two programs together, like 5T and 5E together, we have a decompilation process that we first take the partial program and decompile this into a table sketch. What does it mean? This means we see a small partial visualization, and we're going to find a program and a small table that turns the small table into the partial visualization. And after that, we delegate all the challenge for the table transformation synthesizer, that the goal is to transform the original table to some output that contains the table sketch. So I'll elaborate those in detail and in example later. But the kind of like key takeaway here is that we want to push the challenges in synthesis as far as possible. We are just essentially pushing the containment requirement from the view elements to the containment in the table sense. So that means we only need to deal with the challenge problem in one domain. Yeah, let's see.
I have a question to ask. Can I ask?
Yeah.
Okay. So when you say that the user is required to specify the partial visualization as well, so that you know eventually the synthesis problem is to synthesize the whole solution, the visual part. So do you assume that the user is going to give correct partial solution?
Yeah, we are assuming user are going to provide a correct partial visualization.
Okay.
Yeah.
Okay. But
yeah, there actually is some very fun thing. I will show you later. It's very interesting. Yeah, people don't always provide correct partial visualization, but there's some very fun thing I like when we apply.
So does your approach eventually will lead towards where you can even point out that the partial solution is incorrect?
We don't. As for now, but there are some interesting way how people resolve this themselves.
Okay, thank you.
Yeah. So the key takeaway is that we can push the challenge in the program synthesis as early as possible, so that we just need to build a powerful table transformation synthesizer to do the synthesis task. So how do we do a decompilation? This actually goes into the earlier question about are those visual mapping like one-to-one, right? So this actually is not exactly one-to-one, but in a lot of cases, it's reversible. It's like given your visualization, you can ask a question, what mapping generates the partial program from the data? So for example, if we have a bar chart with 3 attributes, we can imagine there is a small table with 3 columns. One column corresponds to x-axis, another column corresponds to the height, and another column corresponds to color. And then we are asking, getting this partial program, we can just ask what's the data corresponding to this mapping? This is pretty straightforward, right? We have 3 attribute visualization, and we can revert back to a small table that contains like 3 columns and 2 rows. And sometimes there are alternatives. And this is actually a very challenging problem. This is not really a challenging problem, I would say. But there are some like interesting case that the reverse mapping is not one-to-one. So if you think about data aggregation, right? If you want to have a data aggregation that you aggregate all the value with x equals 1 together, then it means you cannot revert it directly. So the way we resolve this is that we restrict the mapping to be almost one-to-one, and then lead those kind of aggregation effort to the table transformation. Just saying when you prepare the data, if you need to do aggregation, you prepare it in the transformation part instead of in the visualization part. So so the key idea here is that we want to formalize the visualization as mappings, and again, leave all the challenges for tables. So the second problem is to synthesize data adapters given this table sketch. If you think about this, if we get the right program that contains the table sketch, then by the way of our design of the partial visualization, we're going to create a visualization that contains the demonstration. So we'll push everything to the table synthesizer. So synthesizing table is a pretty classical problem. So as for example, in the past, I have worked on something about like SQL query synthesis. And one of the key classical algorithms to do this kind of synthesis problem for complex data is to do enumerative search. The way is we start from nothing, and we're going to enumerate programs of size 1. And here the programs are starting from those kind of uninstantiated parameters. So we're starting from some partial programs. And the way we do the search is to enumerate. We enumerate until we find some concrete program. We evaluate the program and compare to the table sketch to see if the output contains a sketch. And then we can just like say something's wrong and then rule it out. And we just go further and further until some point we hit a program that whose output contains a table sketch. So this is a classical algorithm, but I mean, I feel a lot of you are hearing this, you feel a little bit terrified because you know this process is going to be exponential. Even just for like a program of size 1 is already more than what I can fit in the slide. So how do we deal with this? So the key idea is that if you look at this kind of filter program, right? What we do is like we instantiate everything and we notice nothing works. And so essentially we just don't need to, we can reject this sketch. But a better way to ask the question is that can we actually reject this program before we dive into this concrete program so that we don't need to spend computation on enumeration here. So actually it is possible. So if you look at this, let's think about abstractly. So we don't have a concrete program. We don't know what's the predicate we're going to apply to the filter. But we know whatever predicate we're going to have, the output should be something contained by the input table, right? We are just essentially do a filtering. And now if we know this, and if we know the output will be contained by the input table, then if the output is going to be correct, then we must have the table sketch to be contained by the input table as well, right? But here it is not. So it means that filter is apparently not feasible. So we can reject it directly. So actually we can define those kind of abstract semantics for all the operators directly so that we can do this kind of forward reasoning. This is essentially a forward reasoning process is that given the input table and given a partial program, we're asking what's the property of the output and use this property to check against the real output we want to have and use this, if we derive some contradictions, we're going to reject this branch. So we don't need to go deeper anymore. So with forward pruning, this is pretty good, but it's definitely still not enough, especially for some complex operators. And for example, how do we actually reject some more challenging operators like gather? This is essentially a table rotating program we showed earlier, right? So in order to do this, instead of going forward, we're going backward. So how do we go backward? What we know is that we know the table sketch is what we user provided in the red here, right? And so if we know the table sketch looking like this and the partial programming like this, then we can do undo the rotate. Then we know there must be a column that there must be a row 1, 1, 4 to be contained by the input table. And now we can use this to compare to the input table. That input table actually does not contain this row, and we can derive a contradiction that this partial program is not applicable. Yeah, I understand this is a little bit hard to digest, so I actually get some summary here that's try to make it a little bit easier to understand that. So this is essentially the backward reasoning process that we get the output of the demonstration, and we get the partial programs. We're asking what's the property of the input table must satisfy in order to satisfy the constraint. And so we're trying to derive this property and check against the input table to understand whether this sketch is feasible or not. So yeah, so the contribution here is actually to combine this bi-directional reasoning in the search process so that we can prune those abstract programs as early as possible to avoid diving into infinite branches of which we don't want to explore. And here we're still doing the same. If something we cannot reject, we're going to further expand the expression until we find something that hits the correct output. So yeah, so let's just like go over the pipeline again to kind of have a better overview of everything. So we have the input table and the user demonstrate partial visualization. The goal is to synthesize programs to contain this partial visualization. And the program is going to synthesize those two operators to do the transformation such that the final visualization contains what user demonstrated. And also, there's something I didn't mention too much about the potential of multiple pairs can satisfy specification. This is definitely going to happen because the user demonstration is a incomplete specification. So you can have ambiguities that need to resolve. But also, this is also a benefit in our scenario because we are doing visualizations. So the ambiguity means there are going to different visualizations that lay out differently. So the user is actually able to inspect the visualizations to pick which one is correct. We actually get some very interesting results from the user study about this. I will show you in a few minutes. So this is mostly about the algorithm. So we also did a lot of did a bunch of experiment to evaluate those algorithms. This is mostly for us to understand how the algorithm performs. The first question is about tool efficiency. How fast can the algorithm solve some practical visualization problems? And how much ambiguity the visualizations are going to result. So we're adopting a data adapter from the R libraries and visual program from VegaLite. This is a weird combination, I know, but this is kind of the way I like it because it's easier to render. But if you think about the VegaLite is essentially equivalent to the ggplot2. They're just from a slightly different style of syntax. And we evaluated from some benchmarks from Stack Overflow and tutorials. And the way we evaluate is to just set a 10 minutes timeout, and we use partial visualization sampled from the full visualization. So yeah, the input table can be small, but it can also be large. And the program are typically just 1 or 4 statements. This sounds small, but actually, because those operators contains a lot of parameters, they actually quite a lot of decisions to make for each program. So the first is about tool efficiency. You know what I'm going to say? It's going to be pretty good. So what do we do? So this shows the time used to solve the problem with 4 visualization elements. 4 visualization elements just means, for example, if you want to visualize a heat map, you're going to provide 4 rectangles. So we are able to solve 70 out of 83 benchmarks, and a lot of them are within 1 second or 10 seconds. And we also compare the algorithm with a traditional tool that does not use bi-directional reasoning. This is trying to justify the contribution to the synthesis algorithm. And we are able to solve 17 more benchmarks and on average 7 times faster. And for the cases we cannot solve, is either involving large input table and complex transformations. This is actually, especially for the complex transformations, we notice for some operator that require you to do multiple time rotation, then directly from the final output, it's a little bit hard to directly prove because yeah, some of the operators signals get hidden. So yeah, some of the ideas here to help the unsolved cases can be multimodal synthesis, allow user to provide more information. And another thing is about the demonstration complexity. This essentially asks about how many elements does the user need to provide in order to have the correct solution rank well. Yep. Yeah, so here, essentially, we can get 2 things from this chart. It means increasing the size of the partial demonstration. We can get the ranking better because it has less ambiguities. And another thing is that we can also solve a lot of benchmarks with only a small number of examples. This is pretty straightforward. But actually, this is sort of like paper presentation style evaluation. Another interesting thing is about how it actually works in practice. So actually, before showing you some of the interesting discoveries from the study, maybe I can show you how the tool looks like and how the tool works. So the tool is called Falx, and it has a link here. You can just go to play with it right now. And let me just show you a small demo here. So, so we're going to show a demonstration to visualize the temperature difference. So here I get a data set that contains the temperature of New York City and San Francisco from basically in a year. It has a date, and New York has a column, and San Francisco. So let's just show how we can create a visualization to show the temperature difference. So our goal is to create a visualization like this. So we're going to create a line first to visualize the San Francisco temperature, and then we're going to create a bars to visualize the temperature difference between New York City and San Francisco. Yeah, so let me show it here. Let's see. Yeah, can you still see my browser?
No, we're seeing your slides.
Yeah, let me reshare it so you can see my browser.
Okay.
Yeah, you guys see my browser now, right?
Yeah.
Yeah, so this is a tool like I created. So let's see how do we actually do the visualization. So this is a data set that's the same data set I showed in the slides, contains the New York City and San Francisco data. So yeah, so this is a kind of like the main interface of the tool. And what we can do is first to upload the data to here. So you can see everything here. We get a big table with a bunch of data for New York City and San Francisco. Yeah, so the first step is basically try to create a partial visualization. So instead of actually drawing a sketch by hand, what we do is to have an interface allows you to create those elements one by one. So, so if you remember our goal, we want to first create a line chart to show the San Francisco weather. So what we have, we can create a line chart. So the line chart is basically asking us to provide two ends of the line. And so you will connect them together to be a line. So for example, we know the San Francisco temperature in October 1st is 62.7. In October 5, it's going to be 58.7. So here we essentially see a small line segment. It looks a bit boring, but it's a line. So this is essentially a partial visualization. This is very straightforward, actually. So let's just ask a synthesizer, and the synthesizer actually finds some visualization that shows the San Francisco temperature. And there also like another result. I think the other one, the synthesizer tried to put the New York and San Francisco together, but I think we're just going to proceed with the first one. So yeah, so it's good. We get a San Francisco temperature line. And now this second part, we want to use bars to show the difference between New York City and San Francisco. So what we do is to create a bar. We use a float bar because we want the bar to be starting at the San Francisco temperature. So this one first create a bar for the October 1st. So the bar should start from the San Francisco temperature and end at the New York temperature. And we can also use a color to show the difference. So let's do some calculation. I think it's 0.7 difference for those two. So the color, it basically means a darker the color, it's going to show means the temperature is more different. So here is a small bar. It's looking weird in the preview. Actually, a lot of people don't like this, but it's some way to allow you to inspect what it looks like. So we're asking the synthesizer to run again. So now we basically have two layers working together. And the tool actually finds a lot of visualizations. There could be some ambiguities coming here, but it's more like just understanding what it looks like. So yeah, our goal is to have the San Francisco line and the New York line. So we can look at some of those. I mean, this doesn't quite look right because the temperature won't be 5,000. And the first one looks pretty right, I would say. If you look at this, yeah, the first day, the second day shows the temperature and the difference. Yeah, so this one looks right. So,
hey, Chenglong, sorry. Why did the tool generate the second graph? There's no line going down, right? This one, yes.
Yeah, the second graph is kind of weird because we only show the first point in the visualization, right? So the tool may think it can be a potential for doing a combination. So second one trying to summing up the temperature of all the days. So it's always going up. So this is why it doesn't make sense. So actually, if you are not comfortable viewing this, we can also try a different way. We can add a second example to try to do some disambiguate. So we're also going to show the second point for the second point for the October 5th to show what's the temperature difference. So I think the difference should be 5.5 color difference, and we can rerun the synthesizer to see. So if this case where instead of showing only the first bar difference, we also show the second bar to help the tool to disambiguate. Actually, this case is much better because I think the temperature is uniquely defined, and those two differences. The first one only shows the San Francisco data as a line. The second one shows both San Francisco and New York City. And now we essentially get a visualization, and we can do a little bit more customization. So one thing I find kind of interesting to change the bar to rectangle, so it looks a little bit better. And if you want to do some more customization, like you can export this into Vega Lite. So for example, one thing I feel is the chart may be too large, so I can just try to like change the size or something. Yeah, try to do some little bit edit to make it smaller, like what we did. So yeah, so this is how we create a visualization. But the most thing happens here is to create a demonstration and also to synthesize and to pick the result from the visualization. But the tool also has some flexibility, allows you to do some customization with the external because because we're generating programs. We're not just generating a PNG that you cannot edit. So this is how the tool works. Let me share my screen again, my slides again. Yeah, so we get this tool, we get how this works, but actually it's kind of interesting to understand actually how this tool will work in real users' hand, right? So if you think about this is something I told you earlier about all the challenges of R and using R to create visualizations, like difficulty understanding libraries, difficulty of visualization, difficulty of reshaping the data. But there's something I didn't tell you, is that Falx solve all this problem by design. But on the other hand, Falx also create a lot of challenges for you by its own tool. That I didn't tell you. So for example, so essentially now we're having a completely different process. So we don't have those dimensions of like playing with the data or something, but it's actually changed how the way for people to create visualization. So for example, like now people need to, what are the new challenges and how users actually use those tools. So to do this, we actually is in a user study with a bunch of people. Actually, also some people in this meeting participated. Thanks a lot for providing your insight on how to use the tool. So we have 16 participants. This can be data scientists, students, business analysts, and we ask them to solve 4 visualization tasks and to observe what they do. So there are some. So this is essentially a pipeline. There are 3 possible outcomes. When user creates some demonstration, they get a bunch of visualization, and then they select the correct one, or they get nothing. And there are some actually possible confusions from people when they are using the tool. So for example, some people may not be familiar with those visualization concepts. Like they don't understand what is the height of the bar mean, what does the start and end point of the line mean. This may sound trivial for us, but for some people, because they don't have much actual algebra or data experience, so they're actually not very familiar with those. It can be a challenge. And some people are not familiar with demonstrating values because they have been using Excel or Tableau for 20 years. Not 20 years, Tableau hasn't had 20 years. They're using those kind of like Tableau style visualization for 20 years, and then they are not able to create demonstrating values. And some people are not sure how to proceed when they are stuck. And also sometimes a visualization may have too many solutions. It's like what Xingyu asked earlier, how do we actually understand the difference? And some people actually find it hard to distinguish similar visualizations. And there's also a problem about how to validate those solutions. So those are all the challenge of the tool. And of course, from the tool builder perspective, you want to solve them immediately by yourself. But actually what's very interesting is that even though we don't solve the tool while people are using those, people are coming up with a lot of different strategies to interact with the tool to actually solve those problems. So for example, in terms of demonstration, people find some people prefer to do incremental demonstration, and some people try to add multiple points in the beginning to avoid any ambiguity. And a lot of people are also aware of selecting representative examples to avoid ambiguity as well. And in terms of resolving errors, people are coming up with a kind of smart debugging process that try to debug the most recently added elements, or debug by attributes. They want to see if column or size has a problem. And in terms of selecting output, some people use some invariance. It's kind of like similar to what Xingyu talked about earlier. I didn't see anything goes down. So this is why this chart does not satisfy what I'm expecting for the data. So they can rule out some visualizations. And there are some strategies about comparing similar visualization to establish confidence about the result. And in terms of validation, people are often talking about checking some unique points, because they know if you're likely to fake some simple points, but if you have a unique value that you know is correct, they have pretty high confidence. And they also check properties of the visualization for you to check whether the axis contains every element I want. So those are some observations of the strategies of how people interact with this new process. And yeah, there is a little bit idea about how to do this. I think do it better is essentially we can create better interface to support what user want to do instead of building a new pipeline to change everything completely. So yeah, so there are some ideas about this. I feel, yeah, they are not particularly interesting, so I don't want to go too much detail. So yeah, so here it's kind of a summary. From the algorithm perspective, it's mostly trying to solve the compositional synthesis problem and use the bi-directional analysis to prune partial programs as fast as possible. And yeah, so, but I think the more interesting part for you is to try the tool out to see how it works. it's it's going to be pretty fun. So try it out. So the link is here, and you're online. You can just copy the link to play with it. So yeah, so I think how about just go to some chat to, yeah. So I see a question in Zoom.
You want us to read it out for you, or can you see it?
Yeah, I can see it. I'm just reading it now. So some feature from the initial model. Oh, so actually, so actually, this is actually something very interesting. So actually, what we do, we don't really treat the input as a data table. We're just treating it as a table without any constraint. Like we don't know anything about the metadata, because a lot of time we see those examples are from, for example, Stack Overflows. We don't know the key or something. So this is actually something we really want to do is to have those key information or some high-level constraint, because a lot of time when we make a mistake, it's coming from the difficulty of resolving this, resolving, for example, understand something's temperature, right? So we won't be able to, we are not going to summing up temperature because we know the information. So I think this is a good potential. If we know more semantic information about the data, we can make the transformation more more close to what humans do, and can probably get better result. Yeah, we can get a copy of slides. I'll send it to you somewhere. I'll ask Federico to help with that.
Yeah, we'll be posting the whole presentation, like the video of the presentation, on the Program Systems Seminar website.
Oh yeah, that's pretty cool.
What do you mean when you say the semantics of the data?
So yeah, I'm not meaning, so for example, keys like foreign key, primary key, or even better, we know some fine type. We know something is temperature, something is date, something is money. So we can know, if we, for example, we know something is temperature, we know we should not summing up temperature, right? So I feel a lot of this can guide better data transformation, actually.
Okay, and yeah, that was a very great talk and interesting work. So thank you for sharing this.
Oh yeah, thanks a lot.
Yeah, I have a question. So can you also share some future directions that you're pursuing in this area?
Oh, actually, it's very interesting. Okay, so something I skipped here, actually. So actually, one thing particularly interesting here is actually about selecting output. So a lot of people actually, when they are interacting with a tool, so especially from a PO person, right, we always assume we want to make it extremely simple for the user. So user almost don't need to do anything to get everything out. But it's actually not true. A lot of people, even those who have never do program, they are very smart. People are very smart, and they are actually able to guess what the tool is doing. So they are actually interacting with the tool, trying to teach you, selecting better example for the tool and create like better demonstration. So I think one of the most interesting questions is how do we actually actively take feedback from the user? So one example is that some user told me, like, I reject this example already. I don't want this one. Can you actually take this information to help me reject similar errors made by the tool, so that the next time I'm interacting, it's going to be easier? So I think this is one of the very interesting area. And another kind of interesting thing is about the like synthesizing with errors. Actually, people do make errors. So on the one hand, is because they don't familiar with those visualization concepts, or they may even just have typos. It's actually very funny. In my tool, I create a very simple function to check typos. Essentially, if you have some value that's similar to the input table but not correct, I'll generate a warning. It's an extremely simple thing. It's not worth mentioning a technique, but people find it's very extremely useful. So I think how to actually help user to handle those errors is also a very big thing. Yeah, in general for those programming by demonstration tools.
Sure, thank you.
Yeah.
Hi, Chenglong. Actually, I have a related question. Related to the the errors. So I guess for this, for your tool, you do require the specification to be precise, right? So whenever you say there's a point, there's a line, they should be precisely there, right? But for some cases, let's say the data set is very big and the position of the point is calculated through some complicated math, right? Spanning many data points in the data sets. Then that's really hard, right? So I was wondering, in your user studies, or sometimes you talk to people, do you think it's good to make these kind of specifications more imprecise or kind of sort of approximate, right? So for example, they only encode relative positions of 2 points, or kind of a really like a sketchy sketch of the.
Yeah, I think this is actually a very good point, especially if you think about for data that involves aggregation, right? It's very hard to make a precise computation because you need to go through quite a lot of values in order to calculate that. And some people actually talk to this about this in the US study. I think this is one direction is definitely to go like have a take less information, ask you to provide only 1 point something. I think another way to solve those problems is to instead asking user to show you the output, show you the value, can user provide you an expression to do some computation? If you think about this, like in Excel, people are all happy about doing summation over column to rows. Actually, if the user can write you an expression, it means they don't need to do the calculation. It only give you other parts of information that helps you to both retain less ambiguity and also to be precise to solve the problem. Yeah.
Yeah, makes a lot of sense.
Yeah, it'd be interesting. Yeah, so one of my impression actually is like a lot of those program synthesis tools are trying to be simple, but actually we can take more from the user because people like to talk to the tool as well. Who would like to synthesize visualization in other languages? What do they need to do to enable synthesis? Yeah, so there are 2 things. So the first thing is about to synthesize to another library. So that's pretty easy actually. So essentially we have an intermediate representation using mapping. You can view this mapping as a kind of IR or something for visualization, and you can essentially translate the IR to different libraries. And actually I have a partially implemented translation to R library as well. So that'd be easy. On the other part, yeah, the ggplot is actually, I implement part of that. Essentially we just compile the intermediate representation to the ggplot program installed to Vega Lite. That's pretty easy. Another thing is more challenging part is to extend the synthesizer, the data transformation operators. That's the part where you need to write design abstract semantics. I feel that's something, unfortunately, is not likely to be automated, and you actually need to spend some time to think about how to make them good for efficient search. Yeah, but I mean, on the other hand, those kind of basic operators are already supported, so it can already support a bunch of visualization types.
So there's a question from Xinyu.
Oh yeah, using both forward and backward for pruning. What fundamentally prevent you from using just forward? Oh yeah, it's theoretically impossible for some operators. It is because you are getting like extremely abstract way from the input. Yeah, you cannot go forward. So for example, one example is just like, let me think about a good example. Yeah, so the reason is not the preventing you is that you cannot get a concise representation of all the possible output. So for example, if I'm doing a reshaping and I don't tell you which column to reshape on, then the result is essentially there are like 3 totally different type of results you cannot merge into a one compact operator. And if you keep all the branches, then it's essentially just like doing enumeration. So yeah, so the forward and backward is all determined by whether you can keep the property as a concise representation. Yeah, so this is actually interesting. It's not theoretically impossible. It's just like, it's very hard to keep it concise. That requires you to discover better theory or something. Yeah.
That makes sense. That's also what I thought.
Yeah.
All right, thank you.
Yeah.
Can I ask?
Yeah.
Chenglong, can I ask a question?
Yeah.
I'm wondering, does the tool have a sense of what is ambiguous about the input example? So like, in your study, I think there was an example where you had like Emmys, Grammys, all the different awards, and like you're asking the user to create a graph that shows some visualization of the 4 different awards or something, or their sum or something. What if the user gives an example for that basically includes only 2 of the awards rather than all 4? Like, does the tool at the moment, does it have an understanding of the ambiguities, and as a result, could it provide the user hints on like what example should come next?
Yeah, there is a little bit of sense. So actually the way the tool trying to deal with ambiguity in that case is to try to see what portion of data is included. So I mean, the tool prefers to present more data than less. So this is where it kind of suggests you to be more, have more awards demonstrated in that case, and more colors. So, but in general, the tool don't really have a good sense. So for example, like when you provide two colors instead of 4, right? In total you want, do you really just want those 2? Or do you actually want those 2 to represent all 4 awards? So this is something tool does not know, like fundamentally. I think one good way to deal with this case is to have the tool to understand a little bit better about the data. So if the tool can derive those 4 awards in the same category or something, this means that when you do a transformational reshaping, they should be performed in the group instead of as an individual. So if we have that kind of information, we'll make the tool understanding more about ambiguity. So asking you, do you want to be precise or do you want to be general? Yeah, that's something we do not include right now, mostly because I don't find a very common way for people to specify those category information. Yeah.
Thanks.
There was another question.
Yeah.
Yep.
Can I ask a question? Thanks for the talk. So in the scenario where the visualization may consist of 2 complementary plots, do you have a solution in this scenario as well? That user wants to visualize in two complementary plots.
Oh, that's actually interesting. So actually, this tool does not try to think about a complementary result because the tool only try to create a visualization to match you. But I think it's actually possible. I would say this is not directly in the main synthesis loop. It can be after synthesis when you select a visualization. Then the tool can use the visualization knowledge to help you derive the complementary visualization. So actually in the visualization literature, there is a category called anchor-based visualization. What it means, like if you throw anchor visualization as your initial way to explore data, and what you can do is actually to, from that one, to explore similar visualizations, like different style visualization to understand different aspects of the data, or to generate different visualizations to actually like to complement what you already get from the data. So, but today, I think in this anchor visualization, they require you to have the perfect input data provided so that they don't need any transformation. I think it's possible to combine those two. Essentially, you have the first step to teach the tool how to transform the data. And then from that, you're doing the anchor visualization on the prepared data from that. Yeah, that's actually a very interesting idea.
One other thing, so I really enjoyed the comment that you mentioned about learning from user feedback, and that's I guess, the most important feature of it. So I was wondering, have you thought further about a possible solution for that? Like something, because like the user may want to go from one scenario to another scenario, and she may want to preserve this in some sense, some sort of invariant. These invariants maybe can be learned, right? Have you thought about this direction?
I think there are 2 types of the information we can learn from data, right? So one type is essentially like statistical data about what user prefer to demonstrate and what the user like prefer to select. This is sort of an easy way to think about this. I think what is actually more interesting to me is about the logical, the logics the user infer from the interaction. So one of the most interesting questions is basically when user reject you an example. So it means this may be a specific case for this data set. The user, this rejection means that you need to process those 4 columns together instead of separately. So if you can learn that and distill that into a constraint for this data set, and maybe even just for this data set and this user, and then it means for this person in another exploration of this data set can make it easier. So I think that is actually where I find can be very interesting.
Yeah.
People have been using this as a little bit in old days in logic stuff. But
yeah, this connection with logic is very interesting. There was another talk here in this seminar a few weeks ago from another guy from Columbia University that they tried to learn these basically SMT stuff, right? That might be a connection here.
Yeah, definitely. So any more questions? So.
Well, actually, I do have one more question.
Yeah.
So I think this work is mainly addressing the problem of synthesis, right? So for example, like you know what you want to do, and then you don't know how to do it, right? But there is also another space, which is, for example, this kind of business intelligence, right? Where you don't know, you have a big data set, you want to just see what's going on there, but you don't know what kind of visualization you want to use, right? So things like visualization recommendation tools, things like that. So I was wondering how, what thoughts do you have on that problem, and how that problem relates to the problem that.
Oh yeah, this is actually a very good point. So like I think 2 years ago we have a paper on visualization recommendation. So the idea is that, like for example, a lot of people don't really have professionally trained for data visualization, so they're not actually able to create a very good visualization out of the data set. So what we do is actually to allow the experts to write their visualization knowledge in terms of logic constraint, and then we're using those constraints to reason about visualization to recommend to you what visualization you can do on this data set. But there is one problem for that part, is that those logics is also assuming you have a will type input data. So it assumes that your input data is exactly in the right relation you want to present. And from that, it can recommend you, maybe you want to have a line chart is better than a bar chart or something. I think there is an interesting connection here is about how user can specify you about those kind of data shape, data transformations still. So let's say assuming like if you have a input data from from Excel that you want to extract some insight, but the data layout does not reflect the exact relation that you want to show, and it means the recommendation tool cannot actually do it directly. So one way I'm thinking about this is to allow an easy way for people to provide some preliminary demonstration to help you reshape the data to show what you want to present, and then the recommendation is all about the visualization part. So I would say this part is more about creating the anchor that you're going to start further for recommendation. So I think combining those two are, so I mean, in the ideal world, we're going to have one tool that can automatically reshape the data and then recommend everything for you. But I think it's very unlikely to build that out directly because it's like different data are inherently hard to predict how they are, what's the best shape for them. So I think the best place for people to interact is to allow them to show you some relation on the data, and then from that, you transform the data and then start recommendation. Yeah. Interesting.
Yeah. I mean, it seems you're thinking to use first, some sort of demonstration relation, some sort of, some sort of knowledge as an anchor, and then use the recommendation. But I was also thinking the other way around. So you first do recommendation and then do synthesis, right? I mean, basically some sort of repair, right? So basically you use the recommendation to really help the user find a good shape or the kinds of graphs you want to use, and then user can do the fine tuning, using synthesis. So I mean, does that sort of make sense to you?
Yeah, this is kind of cool. I think the only kind of like potential problem is that when you don't have the right data shape out, because essentially there are some knowledge you don't know about the real data set, right? Because you haven't done reshaping yet. So there may be some insight that the tool cannot derive based on the typical knowledge, because the knowledge base is currently based on the relational data, right? So, but I think this is also possible. So for example, if you know some sort of a similar visualization, then you want to enhance that, I think that's totally possible. It's more like just incrementally building incrementally recommendation.
Yeah, exactly. I see.
That'd be cool.
Okay. It seems it really depends on which part we need more help from the user, and then we want the user to kick in for those parts to have. Okay, I see. Makes sense. Thank you.
Yeah. Oh yeah. Actually, just allow user to fix partial visualization if I made a mistake. It's definitely a very, very important part. I mean, right now I only suggest people when they have a typo, but I hope I am able to figure out some way to suggest them better. Yeah.
I guess in your experience with the users, have any users found it preferable or wish that they could pick, say, multiple possible good candidates? Because it seems the demo didn't really showcase that. Is there any use for that?
So actually, there are people interested in saying, so it's actually kind of similar to this recommendation problem, right? People want to, they know a lot about data, but they want to have a different ways to present the same content. But in some sense, like my visualization synthesizer here, when this comes to ambiguity, it's not too much about the ambiguity in the design, but about ambiguity in the data preparation. So there may not be too much value of like selecting multiple results from here. But I think like people are interested in having different ways to present the same data set. I think, yeah, I feel a better ways to kind of do repair or do incremental recommendation from what user presented.
Thank you.
Yeah.
Also great talk.
Thanks. Yeah, so everyone just feel free to try the tool. It's probably gonna break some point or something. But if you find something break, that's a good thing for me to learn.
This is a really awesome talk. Thank you so much.
Yeah.
I think if there are no further questions, then we can adjourn and see everyone next week. So thank you again. Really good work.
Yeah, thanks everyone. I'll post the slides to Federico on the website.
Awesome.
Yep.
This is a great talk. Thanks a lot, Chenglong.
Thanks, Rohan.